After a brief account of phase space, today we are going to discuss a very important concept regarding this phase space, and this is about the density of distribution in phase space. In fact, when you say density of distribution in phase space, that means we are going to define the density of phase points in phase space. This density of phase point in phase space is actually also known as the density of probability distribution, or you may also call it probability density or the distribution function. Actually, this concept is needed to understand a very important theorem of classical statistical mechanics and also the quantum statistical mechanics, and that theorem is known as Liouville's theorem. So before understanding what is Liouville's theorem, we are going to define this probability distribution function, or you can say we are going to define the density of phase point in phase space. As the name says, the density of phase point. So simply when you say density of phase points in phase space, that means this is simply the number of phase points per unit volume of the phase space. Okay? Density of phase point means the number of phase points per unit volume of phase space. Okay? In fact, the dynamical state of a classical statistical system at any given time is properly and suitably specified by the density distribution function rho. So whenever we have to discuss the dynamical state of a classical statistical system, we definitely need the concept of this distribution function or density distribution function rho. So in this regard, it is very important to deal with a dynamical statistical system. Okay. Now let us consider that there is a volume d gamma in phase space. Okay. When you say there is a volume d gamma of phase space, that is also called the hypervolume in phase space. Actually, this volume lies between the position coordinates qk and qk plus dqk and momentum coordinates pk and pk plus dpk. And in this hypervolume d gamma, let us consider that the number of phase points is delta n. So you can say that this delta n is what? This is number of phase points in a volume element d gamma of the phase space. Okay. And if delta n is the number of phase points in the volume d gamma of phase space, then according to definition, what will be the density distribution function? In fact, as the number of phase points per unit volume is called density of phase points, so rho will be simply equal to delta n divided by d gamma. Okay, this is obvious because you can say that in volume d gamma of the phase space, the number of phase points you have considered is delta n. So in unit volume, what will be the number? By unitary method, you can say this will be simply delta n by d gamma. And according to the definition, this delta n by d gamma is denoted by the symbol rho, and it is called density distribution function, or simply the density of phase point in phase space. Okay. Now, if this rho is known and you have to find the number of phase points in a hypervolume d gamma of the phase space, from this equation 1 you can easily say that this delta n will be simply equal to rho times d gamma. Okay. Number of phase points contained in a volume d gamma of the phase space, which is delta n, that will be simply equal to product of this density distribution function rho and the hypervolume d gamma. Okay. Now let us consider a statistical system. When you consider a statistical system, it means there is a system consisting of a large number of particles. A statistical system means a system consisting of a very large number of particles. And we also consider that this system has a degree of freedom of f. As you know from classical mechanics, that if a system of particle has f degree of freedom, that means if our aim is to deal with the state of the system, then we need f independent position coordinates and f momentum coordinates to describe the state of the system in phase space. So we consider that the f position coordinates are qk, where k runs from 1 to f. It means q1, q2, q3, so on qf are the f position coordinates needed to describe the configuration of this this system of large number of particles. And at the same time, we also need the same number of momentum coordinates, and those momentum coordinates will be p1, p2, so on pf, or in brief you can say that the momentum coordinate needed to describe the state of this system in phase space are pk, where k runs from 1 to f. Okay. Now if we think about the density distribution function, that is the density of phase point in the phase space for this system. In fact, in that condition, it is obvious that the density distribution function rho depends on all these position and momentum coordinates. So you can say that the density distribution function rho is a function of the f position coordinates, that is q1, q2, so on qf, and also of f momentum coordinate, that is p1, p2, so on pf. Okay. But as we are considering the dynamical system, it means the phase points are moving, and when the phase points move, then this density distribution function at a given position changes with time. So we can say that not only on the position and momentum coordinates this density distribution function depends, but it also depends on time, because with time at a particular position the density distribution function rho will change, because our system is of dynamical nature, the phase points are in motion. So as a whole you can say that this density distribution function will be actually equal to a function of 2f plus 1 independent variables. Among these 2f, f will be the position coordinates, that is qk, and f will be the momentum coordinates, that is pk, and this 1 is for time t. So as a whole you can say that the density distribution function rho is a function of 2f plus 1 independent variables, and those variables are what? Those variables are f position coordinates and f momentum coordinates and 1 time coordinate. Okay. So in general you can write that this rho is equal to rho of q1, q2, so on qf, p1, p2, so on pf and t. And in brief you can write this expression as rho is equal to rho of qk, pk and t, where k runs from 1 to f. Okay. Now as I have defined the density distribution function in equation 1 like rho equal to delta n divided by this d gamma, where d gamma is a hypervolume in the phase space. Now how this hypervolume d gamma in phase space is defined, you have already learnt in the previous lecture. You know that this hypervolume in phase space is defined like this. This is the product of dq1, dq2, so on dqf, dp1, dp2, so on dpf. Okay, and in brief or in compact form, you can write this expression as d gamma equal to pi over k1 to f dqk times dpk. Here this pi stands for the product over all values of k from 1 to f. Okay, just this summation sign represents the sum of all terms. So here this pi actually represents the product of uh, all uh, all quantities here over all values from k to f. Okay, so d gamma is this much. Now you have seen that the number of phase points in this hypervolume d gamma is delta n, and that delta n you have seen this is equal to rho times d gamma. So you can easily say that this delta n will be equal to product of product from k to f of rho times dqk and dpk. Okay, so this delta n represents the number of phase points in the hypervolume d gamma. Now, if your aim is to find the total number of phase points in the entire phase space, what you will do? It is obvious. If our aim is to find the total number of phase points in the given phase space, and we know the number of phase points in a hypervolume or in a volume element of this phase space, then simply we will integrate for the whole space or for the whole phase space this result defined in equation 4, and that integral will give actually the total number of phase points in the phase space. So for getting the total number of phase points in phase space, you simply integrate this equation 4 for the all space, that is all phase space. Okay, so if you consider that n is the total number of phase points in the phase space, then that n will be simply equal to integral of rho d gamma. Here this integral is actually for the all space, or you can say all phase space. Okay, now instead of this d gamma, we write dq1 times dq2 so on times dqf, dp1, dp2, dpf. So this expression may be written like this, and here the number of sign of integration will be actually equal to 2f, because for each variable dq1, dq2, dqf there will be an integral. So I have written here this dot sign, that this dot sign represents that for each and every variable there will be an integral. Okay, so in this way, if you know the density distribution function rho, then you can easily find by evaluating this integral the total number of phase point in the phase space. Now you will find in the discussion in the forthcoming lecture of different concepts that there are some situations, or there are several situations when we need another distribution function instead of this rho, and that another distribution function is called normalized density distribution function. Okay, so there will be a need to define the normalized density distribution function, and in fact in several physical situations then the use of this normalized distribution function is more convenient than the use of the density distribution function. So I have mentioned it here, that you can see that sometimes it is convenient to work with the normalized distribution function rho n rather than the density distribution function rho. But before using this normalized density distribution function in a particular physical situation, first of all, here we are going to define this normalized density distribution function. So how this normalized density distribution function is defined, we will see. Actually, this normalized density distribution function is denoted by the symbol rho n. Here this subscript n stands for the word normalized, and it is defined by rho divided by n. It means when you will divide the density distribution function rho by the total number of phase points in the phase space, then that quantity will be called normalized density distribution function. So rho n is defined like this. This is rho divided by n, and this rho, as you know, this is a function of qk, pk, and t, and this total number of n you have seen here, that this n is simply equal to integral of rho d gamma, where the integral is for the all phase space. So instead of n, I have written here integral of rho of qk, pk, t d gamma. Okay. Now from this definition you can see what is actually the physical meaning of this normalized density distribution function. As you know, this rho is what? According to definition, this rho is number of phase points in unit volume of phase space. Okay, rho is what? This is number of phase points in unit volume of phase space, and n is what? N is the total number of phase points in the whole phase space. So rho and n both represent the number of phase points, but there is a difference. Rho is the number of phase points in unit volume of phase space, and n is the number of phase points in total volume of the phase space. So you can interpret this rho n just as the probability of measure of the number of phase points per unit volume in different parts of the phase space. So physically, this normalized density distribution function means that it is probability per unit volume of finding of phase points in different parts of the phase space. So rho n is the measure of probability of finding of phase points in unit volume of the phase space. Okay, this is a very remarkable fact. Okay, now we will see that as the name says, that rho n is normalized density distribution function. So it is obvious that this will be normalized, and you know, any normalized function whenever integrated for all space, the result is equal to 1. It means when you say that we are going to find the probability of finding of phase points in all phase space, that will become a certainty, that will be a guarantee, because we are considering the all space, then definitely every phase point will lie in that space. So that will become a surety, that will become a certainty, and so the integral of this rho n with respect to gamma for all space or all phase space, that will be definitely equal to 1, and that is actually called the normalization condition. Okay, but here I have given a very simple proof of this result. You can see, if you want to evaluate this integral rho n d gamma, what will be this result? You can see, instead of this gamma, you can write dq1, dq2, so on, dqf, dp1, dp2, so on, dpf, and rho n is at is, you can see here. And again I have written the number of this sign of integration, which will be actually equal to 2f, for corresponding to the 2f independent variables from dq1 to dpf. Okay. Now as you have seen that this normalized distribution function rho n is defined like this. This is rho divided by n. Oh, rho divided by n, but this n is the total number of phase points in the phase space, so it is a constant factor, and we can take it out from outside of the integral. So this result can be written as 1 over n integral over uh, all space, and that will be rho dq1 so on dqf dp1 dpf. Okay. Now you have seen that this integral actually represents the total number of phase points. You can see it here. The total number of phase points in the phase space. You can see this equation 5. This integral represents the total number of phase points. So instead of that very integral, now you can put n. So instead of this integral, I have substituted here n. So this n and this n will cancel out and result is 1. So what you are seeing here, you can see that the integral of this rho n uh, all over the phase space is equal to 1. So this is the normalization condition, and that's why we simply say that rho n is the normalized distribution function. Okay. Now what this result defined in equation 7, which is the normalization condition, what actually physically it means? When you integrate this rho n for all phase space or for the complete volume of the phase space and result is 1, what does it mean? It means the total probability of finding a phase point in the phase space is equal to 1. So it means actually that the sum of the probabilities of all possible states of our system in the phase space is equal to unity, is equal to 1. Okay. So this was actually the idea of the density distribution function and the normalized density distribution function. Actually in this lecture I have only defined these two terms, but the use of these two terms is actually needed to understand the concept of a very important theorem, as I have told you earlier, and that theorem is called Liouville's theorem. So in the next lecture we will see what is Liouville's theorem, how we can prove it, what is the physical meaning or physical interpretation of this Liouville's theorem, and what are its different applications in the classical physics or classical statistical mechanics. All these things will be discussed in the forthcoming lecture. I hope you have enjoyed this lecture. This was a very short lecture, and we have only explained two terms, but the idea of these two terms have been clear to you. It is my faith. So thank you very much.